Hello everyone, here is Afras Yab. Today we are going to solve Cambridge IGCSE Physics Paper 4 Theory Extended, held on October-November 2019 and paper code is 0625 with variant 43. So let's start from question number 1. Question number 1. Figure 1.1 is the top view of a tank in the aquarium. The tank is filled with salt water. So here is the figure 1.1 and we can see that it's a top view of tank and it is filled with salt water. The depth of the water in the tank is 2.0 meter. Part A. Calculate the volume of the water in the tank. Here we have to calculate the volume of the water. So first of all, we know that it's a cuboid and the volume is equal to the length multiplied by height multiplied by breadth. So I write here volume is equal to length cross breadth cross height. So in this figure we can see that length and breadth is given but height, that is depth, it is 2.0 meter and it is not shown on this figure. So first of all, I draw here So in this figure we can see that the distance from this point to this point, it is actually the height or depth. I write here it is height or depth. So the length and breadth also given and we can calculate the volume, but in this figure we can see that there are two cuboids. Now I am draw a line here to separate these. So this is first cuboid while it is second cuboid. When we have to find out the volume, we have to add the volume of both of these. So I write here volume V is equal to it will be L1, B1 and H1. All of these are multiply plus for second cuboid L2, B2 and H2. By putting values, I can see here the distance from this point to this point is 1.1 meter while the distance from this to this 1.6 meter and it is for first cuboid. So I write here length is 1.6 multiplied by breadth is 1.1 and height for both of these is same. H1 is equal to H2 and it is 2.0 meter. And for second cuboid, length is given and also breadth, it is 3.2 and 1.0. So I write here (1.0) multiplied by 3.2 and H2 is 2.0. So that the total volume comes to be 9.9. The unit of volume is meter cube. So I write here it is equal to 9.9 meter cube. Part B. The density of the water in the tank is 1.1 into 10 to the power 3 kilogram per meter cube. Calculate the mass of water in tank. Here we have to find out the value of mass. And first of all, we know that density is equal to mass over volume. So here we have to find out the value of mass. It will be the product of density and volume. Density is given, that is 1.1 into 10 to the power 3, and volume that we already calculate, it is 9.9 meter cube. So that the mass comes to be 1.1 into 10 to the power 4. The unit of mass is kilogram. So I write here 1.1 into 10 to the power 4 kilogram. Going towards the next part. Part C. Calculate the pressure due to the water at a level of 0.80 meter above the base of tank. So first of all, I consider it's a tank. And this tank is filled with water. It is filled with water. And the total height of this tank is 2 meter. No, this level is 0.80 meter above the base of tank. So this is the base of tank and it is 0.80 meter. So we have to find out the pressure due to the water at the level 0.80 meter above the base of the tank. So that the pressure P is equal to the product of density, acceleration due to gravity and height. So this height, that is the depth of water level, it will be equal to, I write here H is depth of water level, and it will be equal to 2 meter minus 0.80. So that it is 1.2 meter. This depth is actually from the surface to this point. And it will be 1.2 meter. So by putting values, density that is given in last part, 1.1 into 10 to the power 3. The value of G is 10, while the depth is 1.2. So the pressure comes to be 1.3 into 10 to the power 4 Pascal. So I write here 1.3 into 10 to the power 4 Pascal. Question number 2, part A. First, state in words the equation that defines the moment of a force. So here we have to define the moment of force. Moment of force is the product of force and perpendicular distance from the pivot point. So I write here force multiplied by the perpendicular distance from pivot point. Second part, state what is meant by moment of a force. So moment of force is basically the turning effect of force. Right here, it is turning effect of force. Part 3, the force is a vector quantity. Explain what is meant by the term vector. So here we have to define that what is meant by vector. So vector is a quantity that has both magnitude and direction. For example, here is a force. Force is a vector quantity. Similarly, acceleration, velocity is a vector quantity. So I write here the quantity that has both magnitude and direction is called vector. Part B. Figure 2.1 shows a tower crane used to lift a load on a construction site. Explain how the counterweight prevents the crane from toppling over. So here is the figure 2.1 and we can see that it's a crane that is used to lift a load that is attached at one end. So this crane is used to lift the load, and to balance this there will be the counterweight that is on the opposite side of load so that this crane get balance, and this counterweight prevents the crane from toppling over. As the load here causes the clockwise movement, so that the counterweight causes the anti-clockwise movement, and in this way both of these movements are equal and balanced. That's why the counterweight prevents the crane from toppling. So I write here counterweight provides anti-clockwise movement so that the clockwise movement will become equal to the anti-clockwise movement, because the counterweight causes the anti-clockwise movement and the load causes clockwise movement. So both of these movements become equal. I write here so that clockwise movement becomes equal to anti-clockwise movement, so the resultant turning effect will be equal to 0. In this way, the counterweight prevents the crane from toppling over. Question number 3, part A. Figure 3.1 shows a waterfall. Here is a figure 3.1 and we can see that water is falling from height h. And we know that there are two kinds of energy, kinetic energy and second one is potential energy. The formula of kinetic energy is equal to half mv square, and the kinetic energy is associated with the motion while the potential energy is associated with the height. And formula of potential energy is equal to mgh, where m is the mass, g is acceleration due to gravity and h is height. Part 1. Describe the main energy transfer which is taking place at waterfall. So we can see that in figure 3.1 water is falling from height h. So which transfer of energy take place? At the highest point. all of the energy is potential energy, while at ground the height is equal to 0. That's why all of the potential energy is converted into kinetic energy. So I write here, as the water fall, all of the potential energy changes into kinetic energy. So energy changes from gravitational potential energy to kinetic energy. Part 2. The speed of the water as it hits the bottom is 21 meters per second. Calculate the height h of the waterfall. Here we have to calculate the height. So going back to the figure, we can see that at the top point all of the energy is potential energy, and when the water falls, the potential energy decreases while the body gains kinetic energy. In this case, when the water falls from a certain height, its potential energy is decreases and the water gains kinetic energy. So I can simply write as the loss of potential energy is equal to gain in kinetic energy. I write here loss of potential energy will be equal to gain in kinetic energy. So here potential energy is mgh and the kinetic energy is half mv square. This m cancels by this and we have to find out height h. So h will be equal to 1 over 2 v square over g. Now by putting values, it is 1 over 2 and the value of velocity is 21. We have to take its square and divide it by g. Dash value is 10 meters per second square and it is acceleration due to gravity. So that the height comes to be 22.05 meters. I write here 22.05 meter. Part 3. State and explain any assumption you made in part 2. Here we assume that all of the potential energy is changes into kinetic energy. None of the energy is lost to the surrounding. So I write here, we assume that no energy lost to the surrounding. Part B. The sun is the source of energy for most energy resources used to produce electricity. State two energy resources that have another source for their energy. Here we have to state two energy resources except of sun. So we can also gain the energy from our earth. This energy is in the form of geothermal energy. And second one, there is also nuclear energy. Question number 4. Solids have a fixed shape. Liquids adapt to the shape of their container. Gases fill their container. Explain in terms of the forces between molecules and arrangement of molecules why solids, liquids and gases have these properties. So first of all, we know that the molecules of solid are very close to each other and there is no spacing between their molecules. So these are the solid molecules. As there is no spacing between their molecules, so there will be stronger attractive forces. In the case of liquid, there is a small spacing between their molecules and the force of attraction in this case will be smaller as compared to solids. And in case of gases, the molecules are very apart from each other, and there is very small attractive forces between them. So I write here solids, molecules in lattice arrangement It means that the molecules are regularly arranged. As the forces between the molecules are strong. And these forces are strong because there is no spacing between the molecules of solid. For liquid, molecules not fixed in place as the forces between molecules are too weak as compared to solids. And for the gases, the molecules far apart as no force between the molecules. Because in gas, the molecules are very apart from each other, there is a large amount of spacing between them, so the forces are very small that we can neglect them. So there will be no force between the molecules of gas. Question number 5. An electric kettle contains water at a temperature of 19 degrees C. The kettle has a power rating of 3.0 kilowatt and is switched on for 3.5 minutes. So here temperature is given, that is initial temperature 19 degrees C and the power of the kettle is 3.0 kilowatt and time is given, that is 3.5 minutes. Part A. Calculate the energy supplied. Here we have to calculate the energy supplied to the kettle by the electricity supply. So here we have to find out the energy when time, temperature and power is given. So we know that the power is defined as the rate of energy. So I write here power is equal to rate of energy transfer, that is energy over time. Here power is given and time is also given and we have to find out the value of energy. So I write E is equal to P is for power and T is time. By putting values, power is 3.0. It is kilowatt and we have to convert into watt. That's why I multiply it with 1000, that is 10 to the power 3. And time, it is 3.5 minutes and we have to convert this time into seconds. That's why I write 3.5 multiplied by 60. So the energy comes to be 630,000 joule. So I write here electrical energy is equal to 630,000 joules. Part B. At time T is equal to 3.5 minutes, the temperature of the water reaches 100 degrees C. The volume of the water in the kettle is 1700 cubic centimeter and its density is 1.0 gram per centimeter cube. The specific heat capacity of the water is 4200 joule per kg per degree C. Calculate the thermal energy gained by the water. Here we have to calculate the thermal energy. When the specific heat capacity is given, then we use the formula that energy E is equal to mc delta T. Here E is energy, m is mass, C is specific heat capacity and delta T is change in temperature. So initial temperature is given in part A and it is 19 degrees C. After that temperature rises and it becomes 100 degrees C. So that the change in temperature delta T will be equal to 100 minus 19 degrees C and it comes to be 81. So here we have to find out the value of mass because mass is not given. For that we can see here density and volume is given. By using these values I can easily find out the value of mass because density is equal to mass per unit volume. I write here density is equal to mass per unit volume. And we have to find out the value of mass. Mass will be equal to rho and V. Rho is density and V is volume. So I write here energy is equal to rho V C delta T. Now I am going to put values here. So that energy will be equal to density is 1.0 gram per centimeter cube. So I write here 1.0 and volume is given that is 1700 cubic centimeter. Multiply by 1700. So first of all there is a unit centimeter cube for volume and for density it is gram per centimeter cube. We measure the mass in kilogram. First of all, when the unit of density is gram per centimeter cube and volume is centimeter cube. This cancels by this and the unit of mass now is gram. First of all we have to convert this gram into kilogram. That's why I multiply it with 10 to the power minus 3 or I can simply say that I divide it by 1000. So I write here multiply by 10 to the power minus 3 and C that is specific heat capacity it is 4200. Multiply by change in temperature that is 81. So that the energy comes to be 580,000 joules. The unit of energy is joule. That's why the thermal energy will be equal to 580,000 joule. Part C. Calculate the efficiency of kettle. Here we have to calculate the efficiency of kettle and we know that efficiency is the ratio of useful energy output over total input energy. I write here efficiency is equal to useful output energy divided by total input energy multiply by 100. So the useful output energy is basically thermal energy that we calculate here. So I put here 580,000 divided by input energy is the electrical energy that is equal to 630,000 joule. So I write here 630,000 joule multiply by 100. So efficiency comes to be 92%. I write here efficiency is equal to 92%. Question number 6. Figure 6.1 represents wavefronts of a sound wave traveling in air from left to right. So here is a figure 6.1 and we can see that there is a wavefront that is traveling from left to right in this direction. And there are 2 points mentioned, one is B and other one is A. Part A. State the name of given to the part 1. Region around A in the diagram. Part 2. Region around B in the diagram. So in the figure 6.1 we can see that there are 2 points A and B. We can see that point A is located where the wavefronts are very close to each other and it's a longitudinal wave that consists of 2 parts, compression and rarefaction. I write here it's a longitudinal wave that consists of compression and second is rarefaction. Compression is the part of wave where the particles are very close to each other. But rarefaction is the portion of wave where the particles are further apart from each other. In the figure 6.1 we can see a portion that is this one. Here the particles are very close to each other. So this portion is basically compression, but the point B, this portion we can see that the distance between the wavefront is very large as compared to point A. So this region is basically rarefaction. Point A is at compression while the point B is at rarefaction. I write here region around A in diagram is compression because the wavefronts are very close to each other at a point A, and region around B in the diagram here is rarefaction because the wavefronts are very far from each other as compared to A. That's why the B is actually rarefaction. Part B. On figure 6.1, draw a double-headed arrow to show one wavelength. So in figure 6.1 we have to show one wavelength. First of all we have to know about the wavelength. Wavelength is a distance between 2 consecutive compressions or rarefaction. So in this figure we can see that there are different portions where the wavefronts are very close to each other and the wavefronts are further apart from each other. I consider this section, that is compression, and the next compression is at this point. So the distance between these 2 compressions is basically equal to wavelength. I am going to draw a double-headed arrow. So this distance is basically equal to wavelength and I represent it with lambda. Part C. The loudness of the sound increases at the same pitch. So there are 2 words, that is loudness and second one is pitch. Loudness increases but the pitch remains same. State and explain any change there would be in the pattern of wavefront shown in figure 6.1. So first of all, pitch is related with frequency. As given in the question that pitch is same, it means that the frequency remains same, it does not change. And second thing is loudness. Loudness increases. I write here loudness. And loudness is related with the amplitude. When loudness increases, amplitude also increases. I write here amplitude. Both of these are directly proportional to each other. When I increase the loudness, amplitude also increase, and when I decrease the loudness, amplitude also decrease. So, in a figure 6.1, the frequency of the waves remains same because the pitch is same. So, there is a change in amplitude. So, amplitude change means that the portion where there is a compression, there will be more compression, means that the particles come closer to each other. And where there is a rarefaction, the particles will get further apart from each other. So, I'm going to draw here more lines because the amplitude increases. So, the compression also increases. There will be more compressions. And in case of rarefaction, these lines, that is wavefront, will get further apart from each other. So I write here, loudness does not affect the wavelength. We can see in this figure that here in a compression, the number of wavefronts increases, means that the wave compress here. But the distance from this point to this point remains same, which is equal to wavelength. So when we increase the loudness, just amplitude of wave increases, but the wavelength remains same. But as loudness increases, the amplitude also increases. The particles are closer together at compression. And further apart at rarefaction. Part D. The wave passes into water. State and explain any change in the pattern of wavefront shown in figure 6.1. So first of all, there are two medium, air and water. Air is a less denser medium and water is denser medium. I call air as rare medium while the water is denser medium. So when the wave passes from air to water, means that wave passes from rare to denser medium. What will be the effect on the wavefronts? So first of all, their speed increases. The speed of sound increases because water contains large number of molecules and sound waves are nothing but it is just the vibration of particles. So when there are more number of particles, the vibration also increases. As a result, the speed of sound increases. So when the speed of sound increases, there will be no effect on the frequency when medium changes. When a wave goes from air into water, the frequency remains same. Frequency does not change. So according to relation V is equal to F lambda, if frequency is same and speed of sound increases, so that lambda also increases. I write here when speed of sound increases, wavelength also increase, but the frequency remains same. So I write here speed greater in water than air, Therefore, wavelength is greater because frequency remains same. Question number 7, part A. Figure 7.1 shows the position of converging lens, its principal axis, and an object O. In a figure 7.1, this line that is straight, this is basically the principal axis, and it's a converging lens. It is used to converge the ray at a point. And at the position O, we have placed the object. F is the focus point that is on both sides of this lens. Each principal focus of the lens is labeled with F. These focuses are labeled with F. On figure 7.1, draw a ray diagram to locate the position of the image formed by the lens. Here we have to draw the ray diagram that shows the position of image, and we have to label the image with I. So going back to the diagram, when we have to draw the ray diagram, we have to know that how the converging lens form the image. So there are basically 3 lines. First line is that is parallel to the principal axis, and after refraction by the lens, it passes through the principal focus. I write here first ray parallel to principal axis, and after refraction by lens, it passes through F. Now I am going to draw this ray. This is the object. I use a ruler and draw a line. So first of all, this line is parallel to the principal axis, and here by the refraction by this lens, this ray passes through the principal focus. So this is the first ray. Second ray is that passing through the center of lens and travel undeviated, it goes straight. I write here passes through center of lens without deviation. Now I am going to draw this ray. Now I have to draw both of these rays, but these are moving apart from each other. They don't form any image. So as we know that the converging lens form the image, so I just extend these two rays in backward direction, and where they meet at a point, it will be the image. So I'm going to backward extend both of these rays. And I also have to extend the ray 1. So we can see that at this point, both of these rays meet with each other. So this point is basically the point for image formation. So I draw the location of this image. And I label it with I. And these rays are coming in this direction. I also have to put arrows here. Part B. Describe the nature of the image I. Now we also have to describe the nature of this image. First of all, we can see that the height of image is larger as compared to object. So that's why this image would be enlarger. I write here enlarger. Second one, we can see that this object is upright. It means it is straight. So I will write here upright. And in the figure 7.1, we can see that the solid lines does not meet at a point. It means that the image is not real. So we backward extend this ray and meet at this point. So this image is basically virtual image. It is not real image. So I write here it is virtual one. So the image I should be larger, upright and virtual. Part C. Images formed by lenses sometimes have colored edges. Suggest a reason for this. So the image formed by the lenses sometimes have colored edges. First of all, I consider a light when it passes through the prism or any lens, then it will split into different colors. So the image formed by the lenses have colored edges because when the light passing through any prism or lens, then it will split up into different colors and each colors have a specific wavelength, so there will be the dispersion. Right here there will be the dispersion. And why their dispersion happens? So because each color have a specific wavelength due to which it gets refracted by the lens. So I write here sometimes the image formed by the lens have colored edges. It is dispersion in the glass. So I write here dispersion in glass. Question number 8, part A. Figure 8.1 shows a negatively charged conducting sphere. On figure 8.1, draw the electric field pattern around the sphere. In figure 8.1, we can see that here is a charged conducting sphere and it is negatively charged. And here we have to draw the pattern of electric field lines. First of all, if you consider that here is positive charge, then the electric field lines due to this positive charge will be point in outward direction. But for negative charge, the electric field lines will be points inward direction. Because the electric field lines originate from positive charge and it ends at negative charge. So this sphere is basically negatively charged. When we draw the electric field pattern, the electric field lines will be point inward of this sphere. So I'm going to draw this pattern. and all of these lines should be equidistant from each other. So I'm going to draw arrow which is inward. So this is the complete pattern of the electric field due to the negatively charged conducting sphere. Part B. The current in an electrical device is 0.21 ampere. Calculate the charge that flows during a 75-second period of time. So here time is given and also the value of current is given, and we have to find out the value of charge. We know that current is the rate of flow of charges, or we can say that current is equal to charge flow over time taking for the flow of this charge. I can write I is equal to Q over T. Here we have to find out the value of Q, that is charge. So Q will be equal to I cross T. The value of current is given, that is 0.21 ampere. Multiplied by time is 75 seconds. So that the value of charge comes to be 16 coulomb. I write here charge is equal. Question number 9. Figure 9.1 shows a circuit containing an LED and two resistors in parallel, each of resistance capital R. Here is a figure 9.1 and we can see that these are two resistors. This is R and second one is also R. Both of these are in parallel, and there is also a LED that is connected in series with both of these resistors. The normal operating voltage of the LED is 2.1 volt and the normal current is 0.19 ampere. So the current through this LED is equal to 0.19 ampere and the voltage is equal to 2.1 volt. Part A. First, the potential difference PT across the LED is measured with a voltmeter. On figure 9.1, draw the symbol for this voltmeter connected to the circuit. Here we have to draw the symbol for voltmeter. And we know that the voltmeter is used to measure the potential difference and it is always connected in parallel. So here we have to measure the potential difference across this LED. That's why we connect in parallel with this LED. So I am going to draw this. I use ruler. So here I have to connect the voltmeter. It is represented by V. So in this way we can measure the potential difference across the LED. Part 2. The current in the LED is measured with an ammeter. On figure 9.1, draw the symbol for this ammeter connected to the circuit. So ammeter is a device that is used to measure the current and it is always connected in series. So when we have to measure the current, then we connect ammeter in series. So here we connect the ammeter. Part B. Calculate the value of R, that is resistance, when the LED is operating normally. So here we are given the values of normal operating voltage and normal current values. And when the LED is operating normally, then we have to find out the value of resistance capital R. So in the figure 9.1 we can see that both of these resistance, these are in parallel combination and this combination is in series with LED. So the potential through the LED is 2.1 volt and current is 0.19 ampere. So first of all, I write here that in series combination and in parallel combination, which quantity changes and which remains same. So in a series combination, there is a single path for the flow of current, but in a parallel combination, there are more than one path for the flow of current. So in series combination, there are two quantities, potential difference and current. We have to see that which remains same and which changes. So the potential difference in the series combination change, but in parallel combination it remains same. But the value of current in series combination is same, while in parallel combination it changes. Changes means that the total current is obtained by adding all of the current that is passing through the circuit and so on up to IN. Similarly, for potential difference, V is equal to V1 plus V2 up to Vn. So here both of these resistors are in parallel. We can see in parallel combination, the potential remains same. It means that the value of potential difference across both of these resistors are same, which is obtained by subtracting the total potential difference by the potential difference of LED. So I write here V will be equal to 3.7 minus 2.1. So the potential difference across resistor comes to be 1.6 volt. This value of potential difference across this R and also across this R. In both of these resistors, the potential difference remains same because both of these are in parallel combination. We have to find out the value of resistance. For that, we have to know about the potential difference and current. Potential difference that we already calculate, it is equal to 1.6. Second, we have to know about the current. We see here that the total current across the LED is 0.19 ampere. It means that this current passing through the whole circuit. And here we can see that in the parallel combination current changes. It means that when this current passing through circuit, then at that point it divides into two. It may come in this direction or in this direction. So across both of these resistors, the value of current changes and it is different. So the total current across this R is obtained by dividing the total current with 2. Because here at that point the current changes into two paths. So I write here the current through R will be equal to I by 2. And it is 0.19 divided by 2, so that the value of current comes to be 0.095 ampere. This value of current is across this resistor and also this resistor. Now I am able to calculate the resistance because the value of potential difference and current we calculate. So I write here voltage across parallel combination What will be the voltage across the parallel combination? We can see from here. It will be 3.7, that is the total voltage, minus 2.1, that is across the LED. So I write here 3.7 minus 2.1. It is equal to 1.6 volt. Now the current passing through the single resistor. It will be equal to 0.19, that is passing through the whole circuit. It is the current value divided by 2. It comes to be 0.095 ampere. Now the value of potential difference and current is given by using Ohm's law. That is V is equal to IR. I can easily find out the value of R. R comes to be V over I. V is given, that is 1.6 divided by current is 0.095. So that the resistance comes to be 16.84 and it is approximately equal to 17 ohms. So I write here resistance is equal to 17 ohms. So across both of these resistors, the value of resistance will be same. It is 17 ohm and this resistance is also 17 ohm. Question number 10, part A. A magnet and a coil are attached separately to a door and a door frame as shown in figure 10.1. The purpose of the arrangement is to activate a circuit connecting to an LED indicator when the door is opening or closing. This will provide a visual indication that the door is being used. Initially, the door is closed and then it is opened. Part 1. Explain why the indicator comes on and then goes off when the door is closed. So first of all, in figure 10.1, we can see that there is a coil and this magnet. Both of these are connected with the door separately and the magnet has two poles. One is north pole and other is south pole. And the coil is attached with the indicator also, that is LED indicator, and there is also the door frame. So first of all, this magnet has its magnetic field, means it has two poles, south pole and north pole. So the magnetic lines of force will be just like this. I am going to draw these. So if I consider that it's a magnet with north and south pole, so the magnetic lines of force will be from north to south. And there is also a coil that is very close to the magnet. I am going to draw here this coil. So first of all, I consider that when door is closed, so in figure 10.1 we can see that when the door is closed, then this magnet goes very close to the coil. So the magnetic lines of force of this magnet will also passing through the coil, and when the door is closed, then the coil will be at this position. The maximum number of lines of magnetic field passing through the coil, so there will be maximum flux. And we can see here that the flux is changing. That's why there will be the induced EMF, and as a result there will be the induced current that is passing through the indicator, and indicator glows up. Second case is that when we open the door, then the distance between the magnet and coil increases. So the magnet goes away from this coil. When the distance between them increases, so the minimum number of lines of the magnetic field passing through the coil, so that the position of coil will be further away from this magnet. It will be at this position. I will separately draw for the second case. First of all, here is a magnet. It has north pole, and second one it has south pole. And these are the magnetic lines of force. So when the door is open, then the minimum number of lines of magnetic field passing through the coil. So there will be reduction in flux, means that the minimum number of lines interchanging here. So when there is a small amount of flux, there will be induced EMF that will be very small, and the induced current will also be small. That's why the indicator goes off when we open the door. So I write here movement of the magnet relative to the coil. Induces EMF. So there will be induced current. EMF in the coil. So LED glows. Light goes off. When magnet no longer directly below the coil. And this is the case when we open the door. Part 2. The door shuts. The indicator comes on more brightly but for a shorter time than it did in part 1. Suggest and explain why this happens. So here we have closed the door. That is the first condition. Here we also close the door and the magnet behaves like, and there is a magnetic field with south and north pole, and when we draw the magnetic lines of force, they will originate from north and end at south pole. So when we close the door, then the maximum number of lines of the magnetic field crosses the coil, due to which there will be the induced EMF and the current passing through the indicator, and indicator glows up. And there is given that the indicator comes on more brightly. It means that the more amount of current pass through the indicator, that's why the brightness of indicator increases, but for a shorter time. And when the door is closed quickly, the magnetic field lines linked with the coil changes quickly, so that there will be the greater current. And as we know that EMF is equal to change in field line over time. So when the time is shorter, means that time is smaller, then the EMF would be larger. So the induced EMF would be larger. As a result, there will be the large current passing through the indicator and it glows brighter. So I write here, door closes more quickly than it was opened. So the higher current will be in LED. and the magnet moving in a shorter length of time. Next part B. A circuit breaker is recommended for use with a electric lawn mower. State two reasons for this recommendation. So why we use circuit breaker? Because it protect against electric shock, and it is also protect against overheating and its quick response. So I write here because of its protection against overheating and its quick response. Question number 11, part A. The circles shown in figure 11.1 represents three gold nuclei. Three alpha particles are approaching the gold nuclei. So in the figure 11.1, these are the gold nucleus, and this is second one and it is third one. The alpha particles are approaching towards this nucleus. And we know that this nucleus is positively charged, so it has positive charge. On figure 11.1, complete the path of each alpha particle. On first alpha particle, we can see that the alpha particle is approaching toward the gold nucleus and it is going in a straight line. So we know that alpha particles are also positively charged because these are helium nuclei. That's why the both positive charged nuclei repel each other, and the alpha particles will be deflected in backward direction in this case. So I am going to draw its path. It will deflect in backward direction. So I also have to put arrows here. In the second figure, we can see that this gold nuclei is below, but the alpha particle approaching this a higher level above. So that's why the alpha particles will be deflected in this case, but it will be deflected in upward direction. So I'm going to draw its deflection. We have to draw a straight line, that's why I'm going to use ruler. So in this direction, the alpha particle deflects after repulsion by gold nuclei. And in the third case, there will be less deflection, but the alpha particle deflected in downward direction because the gold nuclei is above and the alpha particle approaching is below. That's why it will deflect in downward direction. So this is the path of alpha particles after repulsion by the gold nucleus. Part B. A detector of radioactivity in a laboratory indicates an average of 16 counts per minute when no radioactive samples are present. So the total count rate is 16 counts per minute when there is no radioactive sample. It means that this count rate is due to the background radiation. I write here background radiation count rate. Next, a radioactive sample of half-life 1.5 days is placed close to the detector, which indicates a count rate of 208 counts per minute. So when we place our radioactive sample close to the detector whose half-life is 1.5 days, then the count rate increases by 208 counts per minute. Calculate the count rate that is indicated 6 days later. So here we have to estimate the count rate that is indicated 6 days later. So first of all, the total count rate will be the sum of background radiation count rate plus the radiation from the sample count rate. I write here total count rate will be equal to background radiation count rate plus the count rate of the sample or radiation from the sample. So the total count rate is 208 and the background radiation count rate is 16 counts per minute. So the total count rate at the start or the total count rate of the sample will be equal to 208 minus 16, which is equal to 192 counts per minute. Next we have to find out the total number of half-lives. So I write here total number of half-life it will be equal to the total time divided by half-life. Total time is 6 days, that is given here, divided by the half-life is 1.5 days. So 1.5 days it will be equal to 4. So there are total 4 half-lives. Now after first half-life, half of the sample will decay. So the total is 190 count rate. It will becomes half. After first half-life, it will be 192 divided by 2 and it is 96 count per minute. After second half-life, it will be half of this value. So I write here 96 divided by 2, it will be equal to 48 count per minute. Third one, when third half-life pass, it will be equal to 48 divided by 2, which is equal to 24 counts per minute. And after fourth half-life, it is 24 divided by 2, that is 12 count per minute. So after 4 half-life, the count rate will be 12 counts per minute. So the reading in detector, reading on detector will be equal to this count rate plus the count rate due to the background radiation, that is given 16. So it will be equal to total 28 count per minute. So I write here 28. Next part C. The waste from nuclear power station includes the isotopes technetium 99, tin 126 and selenium 79. These isotopes are radioactive with half-lives of many thousands of years. State the economic and environmental consequences of producing these waste. So all of these elements are radioactive and it is very dangerous to humans and our environment. That's why we must be very careful while dealing with all of these. So they must be stored with shielding. So I write here first point must be stored with shielding. Second one is that must be transported securely. And with shielding. And these are expensive to store. Third one is that in case of any accident, it will be dangerous to people as it emits radioactive radiation.